So I'd like to begin by saying that I'm going to put a link to the MIT OpenCourseWare video that I got the derivation from in the description. The reason being is twofold. First of all, you can double check my work and make sure that everything's accurate. And second of all, I want to show that I'm not simply recreating what they already did. What they did is showed briefly the derivation of theta in terms of arc length, and I'll show you what I mean in just one moment. But what I saw was something not completely different, but something happening underneath, and that happening is the Pythagorean Theorem keeps being used over and over again. And basically everything in this derivation is based upon the Pythagorean Theorem and taking derivatives and integrals on functions that are what I consider to be descendants of the Pythagorean Theorem. Furthermore, the purpose of me showing you this is to help, hopefully, anybody who may be in the position I was in, where you're trying to memorize formulas, because once you understand this, it's a whole other ball game. I don't even deal with notes in class anymore. I just try to understand everything, because once you understand it, it all becomes common sense, and you can handle any single problem thrown at you. And in the real world, you're not going to have a set of problems that you get to study and try to remember and regurgitate onto a piece of paper during an exam. In the real world, you're going to be thrown all kinds of curveballs, and you're going to have nothing to go with except for your instincts and your understanding of the material. So this is to help people not necessarily even understand this specific material, but how to go about understanding it. And to go about understanding it, what you need to do is you need to find the intuition. You need to see the underlying thing that's happening in the background. And that is what I believe Isaac Newton meant by his quote, because if you understand what everything is based off of, it all really is very simple in the end. That is the purpose of this video, to help shed light on that idea, because once you see that idea, you can then strive for the underlying meaning in all of these formulas, even physics, math. It's all based off the same few concepts again and again and again. So without further ado, take a look at this unit circle here. And what I'm going to do first is I'm going to make this just the top half of the unit circle, because we won't have to deal with two equations. We'll only have to deal with one, and you'll see what I mean in 1 second. Now if we draw a hypotenuse here, let's pick a point along the circumference, say right there. So we have the hypotenuse, and as I said, it's a unit circle, so the hypotenuse is a length 1, and let's say we have an angle right here. Angle is called theta, and we have an arc length that will be etched out by that hypotenuse as it moves in this direction right there. Call this arc length alpha. So now what I'll be showing in this video is that alpha is equal to theta. And you might be thinking, I already know that. What's the big deal? Turns out the big deal is this. I always thought that theta was simply defined to be equal to alpha when you're dealing with a unit circle. But it turns out that isn't the way that this comes about. The way that this comes about is that theta is actually derived to be equal to the arc length. And I thought that was pretty amazing in itself, which is why I chose this to be my introductory math video. And even more so, it's a derivation that is exemplar of the idea and the concepts that I'm talking about, how everything is much more simpler and basic underneath the surface. So we know that the equation for the circumference of a circle is c is equal to 2 pi r. And we have a radius of 1 in this case, so we have 2 pi, which is equal to the circumference. And we know that if we go all the way around the circle, we've gone 2 pi radians, and if we go up to this point right here, which is 90 degrees, we've gone pi over 2 radians. Now, as I said, this is actually going to show why that is true, and not just take people's word for it. It's proof. So I'll erase all this, and we'll begin with the law of cosines. If we create a triangle up here, we know that that length is equal to the length down here. And we'll call this x, since it's along the x-axis. We know that the height at that given x is represented by the y-coordinate right here. We'll call this length y right there. And we know that the same red line up there for that length is exactly equal to this right here. And that's equal to whatever the x-coordinate is at this point, at this random point that we picked. So let's say that we have an angle psi right here. And we know that that's a right angle, because we're dealing with a unit circle that is set up to deal with right angles for this specific reason. We know that with that angle psi, we have, by the law of cosines, the side h squared is going to be equal to the length x squared plus the length y squared minus 2 times x, y, cosine of the angle between them, which in this case is psi. Now, because it's a right angle, cosine of psi is equal to 0, so we have 2xy times 0. This drops out, turns to 0, Then we have h squared is equal to x squared plus y squared, which is known as the Pythagorean Theorem. The Pythagorean Theorem and the Law of Cosines are not two separate entities. It's not as complicated as that. It's simply that the Pythagorean Theorem is a special case of the Law of Cosines when you're dealing with a right angle. I'd also like to make two additional remarks at this point. The first one is, if you replace h with r, what you'll be looking at is the equation of a circle centered at the origin. And if you replace that h with a z, z representing a third axis coming up out of the screen you're looking at right now, what you would then have is an equation of a cone with the tip of the cone at the origin, and as z gets higher and higher or comes closer and closer towards you, the cone will become wider and wider. And if you go into the page in the negative z direction, the cone will also get wider and wider the further down you go. So what that would look like, again, would be a mirrored reflection of a cone with the tip at the origin. Now, even though these three equations, the Pythagorean Theorem, the equation of a circle, and the equation of a cone, all have different names, in essence, they truly are all one and the same. And if you happen to be interested in a more in-depth explanation of the equation of a circle and a cone and what they truly represent, I'll be making a video on that as well, and you can click the link in the description. So now that we have this equation right here, known as the Pythagorean Theorem, what we will do is solve for y. We know that h is equal to 1, so we'll just simply write 1 minus x squared. In the plus or minus sign, because we deleted the bottom half of the circle, we only have to deal with the positive part. We don't have to deal with the negative at this point. The next step is to find the derivative of y with respect to x. Now we know that we can do that because if we look up here and we bring x towards the origin right here, we could end up with a point, let's say right here. Now that new x coordinate, we'll call that x1, will correlate with a point along the circumference of the circle right about up here, which will give us a new y at that height up there. So y will now be up here, and as you can see, clearly different than that height right there. Furthermore, with the hypotenuse now being up here, we can see that alpha is now shorter as well, because this segment up here is no longer part of alpha, or the arc length. The arc length is now this section right up here. So with that, we can see that both y and alpha are functions of x. As x changes, y and alpha change respectively. So let's find out what the derivative of y is as x changes. Y prime is equal to negative x over 1 minus x squared to the 1/2. And that's it. That's the derivative of y with respect to x. So the next piece of the puzzle is to find the arc length formula. The purpose of this video isn't necessarily to show the derivations of these formulas. The purpose of this video is to show the underlying happenings beneath the surface in the derivation of these formulas. Now, the derivation of the arc length formula is slightly intensive, and if I were to go through the formal derivation right here, right now, it would greatly take away from the purpose of this video by basically getting focused on the trees and not the forest. What we're looking at here is the big picture, taking a step back and looking at what's happening beneath all these different formulas. Now, there's an intuition behind the derivation of the arc length formula, and I'm going to stick with that specifically for this video. An extension of that intuition is going to be a video that I'll put a link to in the description showing the actual formal derivation of the arc length formula. But as I said, for now, we're going to stick with the intuition because I don't want to take away from the big picture, which is what this video is really about. So, aiming for the intuition behind this, it is absolutely based off the Pythagorean Theorem. And if you click the link in the description, if I've made that video, by the time you're watching this one, you'll definitely see that it really is rooted in the Pythagorean Theorem. And if I haven't been able to make that video yet, you can do a search on YouTube, and I'm sure you'll be able to find a couple of them. That being said, what I've drawn here is a blown up corner of the unit circle. And we can think of this right here as the x-axis. Here's our angle theta right there. We have the hypotenuse right here. We have the y for the height, and we have the x down here for the x coordinate. Now, this length right here, I'm going to call delta x. And we're going to bring this delta x in so that it ends up being equal to 0. Now, as that happens, the hypotenuse is going to travel down this way. And eventually, it will get down in this corner. As we begin to get closer, that hypotenuse right there, we're going to see that everything begins moving in to this point right here, when x will actually equal 0. That's where everything is going to. Everything's moving in that direction. We'll have the new y right here, much lower. And we'll have this orange line right there, creating the triangle. That's going to be even closer to here. I'll erase that so you can see it a little better. That's going to move in even closer also. And you can see that gap, the black gap between the orange and the yellow line, is going to get smaller and smaller. So this yellow line, we're going to call it S for arc length, because in the arc length formula, arc length is almost always represented by the variable S. So we'll use that. But as you can see, as delta x goes to 0 right here, everything moves in that direction and downward in that direction. And as delta x gets closer and closer to 0, the hypotenuse is going to come down further and further. That gap is going to get smaller and smaller. This orange line is going to move further and further that way, and so is the green line. And as that does, the green line is going to get shorter and shorter. So everything goes into this point right down there. Now, if we take the limit once delta x approaches 0, what we'll be left with is the differentials. So at that point, the length of the orange line right there and the length of the yellow line right here are going to be indistinguishable from one another. They'll virtually be the same line. Now, the way that you can think of extracting the actual tangible arc length as a numerical value is this. If we can come up with a formula that encapsulates this area right here, which happens to be a right triangle, and we take the limit of those variables as delta x approaches 0, we will be left with the differentials. And if we integrate those differentials along this domain right here, the x-axis, what we'll essentially be doing is integrating that function as the hypotenuse etches out this line S right here. If we sum all those infinitesimals up, what we're left with is a numerical value for the arc length. These differentials are conceptual. They're not actual tangible numbers. The beauty of calculus is that through calculus, we can come up with tangible numbers and solve real-life problems using differentials, but the fact of the matter is that the differentials are not really numbers. They represent a small change to an input of a function, resulting in a respective change to the output. Now, we saw before that arc length in the first picture, which was alpha, and in this case it's s, and the height y, are both functions of x. They both change with respect to x. And if we call this orange line right here delta s, we can see clearly that delta s changes as x changes as well. And that right there is where the formula for arc length is derived from. Now, I'm going to clean this up and we'll go back to the original picture that I had. So what we'll do now, because y and s are both changing as delta x goes to 0, I'll call this delta y as well. Now, as you know, the definition of a derivative involves taking the limit as delta x approaches 0, and that is how the derivative actually comes about. So I'm going to skip that step, put the link in the description, and we'll proceed forward upon the foundation of the intuition we just built. So we know, again, by the Pythagorean Theorem, that this delta s squared is going to be equal to delta x squared plus delta y squared. And if we solve for delta s, what we have is, and skipping the formality, which is explained by the link in the description, we'll be left with this. ds is going to be equal to dx squared plus dy squared. We have the square root of all that. Now, the next step that I'm going to do is I'm going to treat these differentials as if they were actually numbers. And the fact of the matter is, you can absolutely do that. And I'll be putting a link for that proof in the description as well. Side note here, ds, dx, it's called Leibniz Notation. It's developed by Leibniz himself. And the countries in Europe that began using this Leibniz Notation actually advanced their mathematics by about a few hundred years over the countries that were still using the Newton notation for differentials, because you can actually treat these as if they're numbers. And when you begin treating them as if they're numbers, you're actually able to do what we're about to do right now. Whereas before, using the Newton notation, you were unable to perform these type of operations. What the Leibniz Notation lets you do is treat these as if they're numbers with basic multiplication properties, meaning that if we set this equal to 1 and we multiply each side by dx, which technically you can't do, but at the same time you can, and that's what the proof is on. So check that link out too if you're interested. So then we have ds is going to be equal to dx, and like I said again, you can absolutely do this. And so what we'll do here is go like this. We'll do ds is equal to, we're going to factor out the dx right out of the radical. So we have dx, because it was squared inside the radical, so it's not here, it's going to be equal to 1 plus, and we have a dy squared over dx squared, so I'll just write that as dy over dx quantity squared. And we'll switch around the ordering, and we'll write dy dx as y prime. So we have ds is equal to 1 plus y prime squared dx. And now we've already solved for y prime, so we'll plug that in. Y prime is up here, and it was equal to negative x over 1 minus x squared to the 1/2. So we have ds is going to be equal to 1 plus negative x over 1 minus x squared to the 1/2. All under the radical, and this whole quantity right here squared dx. Now let's simplify this right here. And we plug that back in to what we set ds equal to. So if we have a right triangle right here, and we have x, and we have y, we set this equal to 1. By the Pythagorean Theorem, we have x squared plus y squared is equal to 1 squared is equal to 1. Now we also know from the most basic trigonometric identities that cosine of theta, if this is theta right there, is going to be equal to the adjacent over the hypotenuse, which in this case is equal to x over 1, which equals x. And we know that the sine of theta is equal to the opposite over the hypotenuse, which is equal to y over 1, which is equal to y. So if we plug this in right here to this equation right there, we have cosine squared theta plus sine squared theta is going to be equal to 1. So the trigonometric substitution we'll be using here is again rooted in the Pythagorean Theorem. So what we'll do here is we'll solve for cosine. We'll be setting x equal to sine. So if x equals to sine theta, we know that dx d theta is going to be equal to d theta of sine theta. And that ends up being equal to, and if we treat these as if they were numbers using the magic of Leibniz Notation, multiply each side by d theta, we get dx equals to cosine theta d theta. So we have everything we need. Have this right here, have this right here, and have this right here. So let's make the substitution. Now we're left with ds is equal to d theta. So at this point, I think it's best to proceed forward with the integration so that we can get s as well as theta. So we'll integrate both sides. Integral of ds is equal to s. The integral of d theta is equal to theta. And we need the constant of integration because we're dealing with an indefinite integral. And that's it. So we have s is equal to theta plus c. And this is pretty close to what we were aiming for. We wanted to show that theta is actually equal to s by deriving it, not just taking our professor's and our teacher's word for it. So with that being said, let's go ahead and solve for theta using this right here. So if we said that, I'll bring this down here. X is equal to sine theta. And we take the inverse sine function of both sides. And I'm going to rewrite the sine inverse as arcsine, just because that's the way I prefer to see it. And then we'll plug this back in up here for theta. Now at this point, we have the constant c because we did indefinite integrals. But if we think back to the original problem that we were working on, we actually have bounds of integration that we can use. So what we can do is we can erase this plus c right here, so long as we perform the bounds of integration. So to find the bounds of integration, what we'll do is we'll go back up to the beginning. Alright, and I'm going to clean this up to how we had it originally because it looks a little confusing like that. Since we have arcsine of x, what we'll do is we'll just change this to a, and we'll perform the integration on the domain of x between a and 0, right there. And that will give us the arc length right up here. And we'll also change the s to alpha, because that's what we're using for the variable for arc length in our specific problem. So we have from a to 0, and we'll set the s equal to alpha. So now we'll solve for this definite integral, and we know that this is equal to 0. So we have alpha is equal to arcsine of A. And at this point, we're at the home stretch. Now, what we'll do here is we'll flip this back to be a function of sine by taking the sine of both sides. So we have the sine of alpha is going to be equal to the sine of arcsine of A, which will be equal to A. So the sine of alpha is equal to A. Now this right here might not seem like much at face value, but if we look at what it means, it actually means a lot. So I'll scroll down here and I'm going to draw another unit circle. Alright, so now we have a replica of the original picture, and what I'll do is drag this part down a little bit, bring it in view, because that right there is what it's all about. So what exactly does this say? We know that the sine of an angle is equal to the opposite over the hypotenuse. So in this case, we have the sine of theta is equal to the opposite, which is the same as this right here, x is equal to a, over the hypotenuse, which is 1, which is equal to a. Now, we have something very interesting here. We have right here sine of alpha equals a, and we also have right here that the sine of theta is equal to a. Alright, so that means that if they're both equal to a, then they're both equal to each other. We have a equals sine of alpha is equal to sine of theta. So there we go. So the sine of alpha is equal to the sine of theta. And the only way that that's true is if alpha is equal to theta on the domain of the arcsine function. Now right there is the kicker. That's what it's all about. That's the conclusion of all this. That is the derivation of theta to be equal to the arc length. That's where the definition comes from. And I find this to be one of the most amazing proofs that I've ever seen in my life. And furthermore, the fact that we used the Pythagorean Theorem over and over and over again to get here is what I find even more mind-blowing than that. That is the conclusion of all this. I'd also like to finish by saying I found all this out by watching videos on my own. And I say this to you not to talk about myself, but to offer you hopefully inspiration to teach yourself like I did. And I'm almost done with the computer engineering degree. I've taken multivariable calculus, linear algebra, your standard higher level math classes, and to be honest, I learned next to nothing in class. I learned everything on my own. At home, watching Khan Academy, MIT OpenCourseWare, places like that, and it's all free. And the education quality that you get out of those resources are the absolute best you can get. Another really good website that I found recently is edX. I'm actually enrolled in about 7 different classes on there right now, but in conclusion, I really hope that this helps you. I hope this helps you see that things aren't as complicated and complex as they seem on the surface, and that underneath, they really are just basic themes over and over again. And I know I've said it again and again and again in this video, but my intent is to really drill it in your head so that you never forget exactly what Isaac Newton said, in that truth is ever to be found in simplicity and not in the multiplicity and confusion of things.